I need everyone's attention here. Make sure you're focusing, because I'm adding one more thing to the mix, as though you needed that at the moment. So let me make sure this is recording. Now I'm nervous. Okay, there it is. All right, so we've got, where's my full screen? We've talked about how to convert from moles to moles. We've talked about how to convert from moles to grams. We've talked about how to go from moles to particles, grams to particles, all that stuff, okay? The one thing we're going to add on top of that is volume problems, okay? And there's one conversion, well, actually, I guess there's two conversions that are going to allow you to get back and forth between moles and volume. What's that? Oh, you know what? I printed off your guided notes before I had put this in here. So you're probably just going to have to put this on a separate sheet of paper. I apologize. Or you can write it on the side if you have room. That's fine. Or you could just not. Those are your three options, I suppose. Well, there are other options, but let's not discuss those. Okay, so, and you don't necessarily have to write all of this down, okay? I would write down the first thing for sure, because you're going to need this conversion factor, all right? Do you remember talking about this when we talked about gases? Standard temperature and pressure, 1 mole of gas is 22.4 liters. So guess what? In a stoichiometry problem, that would allow you to get from moles to volume, all right? So that's one extra conversion factor that you can use. Now, another one is density. If I give you density in a problem, okay, density is calculated in grams per milliliter, that's the unit for density. So you can actually use that as a conversion factor to get back and forth between mass and volume.
So will we have to memorize 22.4?
I would remember 22.4, yes. Okay. 1 mole of gas is 22.4 liters at STP. Only at STP. Standard temperature and pressure, or stone simple pilots, depending on what decade you are from. Probably for most of you, it's just standard temperature and pressure. Standard temperature is 0 degrees Celsius, which makes no sense to me. Let's make it the freezing point. And then standard pressure is 1 atmosphere. That makes sense to me because that's the pressure that is being exerted on us right now. Approximately. All right? So those are the two things that you need to remember that will help you to do any of the volume problems. And that's really it, okay? Once we know those two things, we can do any of the volume problems we need to do. I just need to show you some examples now. All right? Everybody ready? I know you had to kind of write that down from scratch, so. Okay, so here's the problem. And yeah, well, here's the deal. You can or you don't have to. I'm making a video on this right now, so you can always go back and reference the video if you needed to know what the problem actually is. Or, I don't know, yeah, whatever you want to do. It's going to be easier later if you write it now, I would say. But there's always a way to get to it if you don't write it now. That dash right there, that's just a subheading from the bullet, so it's not like a minus sign. I'm not adding something weird to your chemical equations here. Well, that's a good question. And the answer would be, doesn't look like it. If you look at the aluminum, right? That aluminum doesn't look balanced to me. So that's just to remind you, when we do stoichiometry, the first thing we need is always a balanced chemical equation. All right? So let's balance it quickly, and then we can do whatever else we need to do with it. Any ideas here? 4 on the right for aluminum. Okay. What else? Okay, let's balance the carbons first, just because it seems like that's going to be a little easier for me. If I put a 3 here. Okay, so now let's see if we can balance the hydrogens and the chlorines at the same time. Okay. Does that do it?
Does it?
All right. So that wasn't that bad. It could have been if you went in the wrong order, I suppose. All right, so now we've got our coefficients in our balanced chemical equation. Now we can do the rest of the problem. It says how many liters of methane would be produced. I guess one thing you'd have to know is what is methane. I'll bet we can figure it out, though. Process of elimination here. What would this one probably be called?
Aluminum carbide.
Right. This is probably the aluminum carbide, right? Okay. What's this one called?
Aluminum chloride.
Aluminum chloride, right?
Oh, it's CH4.
So, yeah, and we know this is HCl. Hopefully you've seen that enough now that you know what that is. What's HCl? Hydrochloric acid, right? Or hydrogen chloride. That is another way to name it, okay? So that leaves CH4. That's probably our methane, right? Now, on a test or quiz, I would actually tell you what it is, okay? So we want to know how many liters of methane. We're starting with 4.5 grams of aluminum carbide. So 4.5 grams of Al4C3. Any ideas for what we do first?
Grams to moles. So grams to moles, yeah.
Okay, get to moles. That's always a good bet, right? So grams of Al4C3 to moles of Al4C3. Should have told you this before you started. You might want to write small on this one.
Grams to mole. I want 6.8.
Okay, so yeah, so aluminum's 26 point, is that right, 982? Yeah, that's right. Times 4 plus 3 carbons, which carbon is 12.011. Yep, 143.961. That's our molar mass. All right, right now we have moles of Al4C3. Okay? Let's take it one step at a time. So now we've got moles of aluminum carbide. What are we eventually working our way towards here?
So we're going to go from moles of Al4C3 to moles of methane.
Okay, that makes sense to me.
So you're going to have 1.
Okay, so 3 moles of CH4 for every 1 mole of Al4C3. Okay.
And then we would go from moles.
Okay, can we go from moles to liters here? When can we go from moles to liters? Let me back up one here. Well, yes, when it's a gas, which CH4 is a gas, okay? Has to be at STP. Does it say anywhere in the problem that we're at standard temperature and pressure? No, it has to say that for you to be able to use that number, okay? It'll just tell you at STP in the problem, but standard temperature is 0 Celsius, standard pressure is 1 atmosphere. I don't necessarily expect you to know that for the stoichiometry problems. I expected you to know that when we were doing the gas law stuff, but... Okay, so we can't go from moles to liters here.
So we're going to use the density of methane.
Okay, we're probably going to use the density of methane. I'm guessing they gave us that for some reason.
So we're going to go from moles to grams.
Moles 2 grams of the CH4. Okay, let's give that a try. This one's tricky. I might save this for a bonus type question on your test. Let's see, carbon is 12.011 plus 4 of the hydrogens, which is 1.0079. Yep, 16.0426. I'm going to say 16.043. Technically, that's the right number of 66 because we added those together. But the main reason I did that is because I didn't have room for it. I know, I'm really not trying with my noises anymore. I got to come up with a new noise. Yeah, I'll do the laser sound, okay? What's that?
You're like really energetic. Like
You just have to get used to it. I don't Okay, so now we need to go from grams of CH4 to, can we do that?
I don't know. Grams of liters.
I mean, we got to get to liters somehow, right?
Grams.
This right here, the 0.554, another way to write that is that's how many grams there are in 1 liter, right?
Oh, then yes, do that.
So let's do that, okay? I like it when people get excited about chemistry. All right, so, well, I was just saying I like it. Okay. You guys are not saving this. All right. So we've got 1 liter, right? And there's 0.554 grams in every 1 liter. So we can put the 0.554 grams down here. Oh, whoops. I mean, pew, pew. Sorry. That was a really low-sounding laser. I don't know. All right. So now we're done, right? Because that's what they're asking us for is liters. That only took about 7 steps. Yeah. Should we, I feel like, I don't know, should I play the Dora song or something every time that we solve a stoichiometry problem? We did it. We did it. All right. Dora. Okay, so now we just have to work this all through. So you take the 4.5 divided by 143.961 times 3 times 16.043 divided by 0.554. How many sig figs in our answer? 2. That's what we started with, right? So 2.7 is what I'm getting, if I did that right. 2.7 liters of CH4. All right? If it's not at STP, you're going to have to given a density in order to be able to figure out the volume. That's the kind of problem you probably don't want, okay? The STP problems are much easier than that. So let's do an STP problem. Okay, phosphorus P4 burns in oxygen to form diphosphorus pentoxide. Boy, I'm just being really hard on you right now. Write and balance a chemical equation representing this chemical reaction. Okay, so I told you it's P4, so, well, that's supposed to be a subscript 4, sorry. So P4 burns in oxygen. What's oxygen? O2. To form diphosphorus pentoxide. What is that? P2O5. Balanced? No. 2 here, that'll take care of our phosphorus. And 5 in front of the O. Good. All right, now we're good. How many moles of diphosphorus pentoxide are formed by the combustion of 3.2 liters of oxygen gas at STP? All right, we're at STP. Now we can use that 22.4 number. All right? So what are we starting with here? 3.2 liters of oxygen gas, so that's O2. Okay. Now this is kind of a ridiculous problem, to be honest with you. I was stretching here. Combustion's not going to happen at STP. Combustion doesn't typically happen at 0 degrees Celsius, but just go with me on this, all right? I just wanted you to know that I understand it's ridiculous. So liters of O2 is what goes on the bottom. Then what? Well, tell me units. What are we going to go to here? Can we go to moles of O2 from liters of O2? On this one, yes. Why? Because we're at STP. Okay, so in 1 mole of O2, how many liters are there? 22.4. All right? Pew, pew. That was better. Okay, you want to make the noise every time that I'm crossing it out? Okay. I'll just give you a signal. All right. So now we're going from moles of O2 to what? Moles of diphosphorus pentoxide. Yep. And the mole ratio here comes from the chemical equation, all right? 2 to 5. You ready?
Yeah.
Faked you out. Okay, you ready? Really? Really?
You go. You got it, Mr. Come on.
I'm sorry, I shouldn't have faked you out like that. That wasn't nice. Okay, now we have moles of P2O5. What are we trying to get to here?
The moles.
Oh,
So we're done.
so we're done. That was easy. See, my diabolical scheme here is to get you to a point where you're happy with a 2-step problem. Because normally they're 5 steps. Earlier in the year, you would not have been happy with a 2-step problem.
Yeah. Earlier in the year, it was half of 1 step. I was like, what am I doing?
Yeah. You guys are so much smarter than you were then. You really are.
Thank you.
Man, you were... No, never mind. Okay, so 2 sig figs, right? So I'm getting 0.057 and then some other stuff, but the other stuff doesn't matter because we just need 2 sig figs. Am I right?
Yep.
Okay. Of P2O5.
P2O5.
There you go. All right, so that's that. Let me give you the worksheet, and I'll tell you which ones that you guys really want to focus on. Yes, sir. Where did I get 22.4 from?
The value of 32.
I really just kind of pulled that number out of thin air, sort of. It's a number that it comes from experiments that scientists have done at standard temperature and pressure, and they realize that any gas is takes up 22.4 liters of space if there's 1 mole of that gas. Yeah. Here's why. Yeah, you were supposed to know that. Okay, so that's it for the volume stuff. Does that make sense?
Yeah.
We okay? The problem is it's just adding one more thing onto a list of already fairly long things you have to remember, okay? But that in and of itself I don't think is too bad.